Welcome to The Explainer. Today, we're putting on our detective hats. We're cracking open a scientific paper from the 1980s to solve a microscopic mystery, one that's hidden deep inside a material you see every single day: steel.
All right, so what's the big mystery here? It really boils down to a pretty simple question about what's happening deep inside steel. Are the carbon atoms in there friends, or are they foes? Do they like to hang out together, or do they try to keep their distance?
To even start to answer that, we've got to shrink ourselves way down to the atomic scale. Because if you could look inside a piece of steel, you wouldn't see a solid, uniform block. You'd actually see this incredibly organized crystal structure made up almost entirely of iron atoms.
And this specific iron crystal, this framework, has a name. It's called ferrite. You can just think of it as the basic room or the house that makes up most common steels. It's the environment where all our little carbon atoms are living.
So, let's run with that idea. Let's imagine these carbon atoms are all guests at a party inside this big ferrite room. The huge question for scientists for the longest time was, well, what kind of party guests are they? Do they all huddle up together in a group, or are they the types who prefer their own personal space?
You know, for a very long time, the scientific community was pretty sure they knew the answer. There was this one prevailing theory about how these carbon guests behaved, and pretty much everyone just accepted it as fact.
See, the established thinking all came from studies on a slightly different type of steel, something called austenite. And in that environment, it was totally clear that the interaction energy between carbon atoms was, and I quote, large and negative. Now, in the world of thermodynamics, negative energy means one thing: attraction.
So for years, the scientific models for ferrite, the steel we're talking about, they just kind of borrowed that idea. The assumption was, hey, it works for austenite, so it must work for ferrite too. Everyone figured the carbon atoms were drawn to each other, forming these little clusters.
But here's the thing. Great science is all about questioning assumptions. So in 1980, a materials scientist named H.K.D.H. Bhattacharya decided it was time to really put that old idea to the test. He decided to take a completely fresh look at the most accurate data he could get his hands on.
And he didn't just make a new guess. No, he went right back to the fundamentals, digging deep into the really complex thermodynamic math that actually governs how these atoms behave. This is the real, painstaking detective work of science. You gotta check the math.
His entire investigation, the whole mystery, really hinged on calculating one single value, that interaction energy, which we write as omega k. Think of it like a signpost. If omega k is a negative number, the atoms attract, but if it's positive, they repel. Simple as that.
And this is what he found. He plugged in the best data available for different temperatures and reran the numbers. And just look at the column on the right. A really clear trend popped out. At almost every single temperature, the value wasn't just positive, it was a huge positive number, pointing in the complete opposite direction of that old assumption. So what was the final verdict? Well, this fresh look at the data led to a conclusion that would completely flip our fundamental understanding of steel on its head. The analysis showed that the interaction energy wasn't negative at all. In fact, it was a massive positive number, over 83,000 joules per mole. And in thermodynamics, a strongly positive value like that means only one thing: a powerful repulsive force. This finding was a total 180 from what everyone had believed for so long. Instead of an attractive force pulling atoms together into clusters, it turns out there was a repulsive force actively pushing them apart. The sign flipped from negative to positive, and with it, our entire understanding of what's going on.
So, let's go back to our party analogy. Turns out the carbon atoms aren't social butterflies at all. Nope. They're the guests who deliberately stand in different corners of the room, making sure they keep their distance from each other. They really value their personal space.
Now, you might be sitting there thinking, okay, so they push each other away. Cool, but so what? Why does any of this actually matter? Well, it turns out this seemingly tiny detail about how atoms behave has absolutely massive implications for how we design and build things.
For starters, this discovery meant that all the thermodynamic models people were using to design new steels were based on a flawed idea. Understanding that carbon atoms actually repel each other gave scientists a much more accurate foundation to work from. It confirmed that once a carbon atom takes a spot, it basically puts up a do not enter sign on all the spots right next to it. And here's the real bottom line. When your fundamental models are more accurate, you can get way better at predicting how a material is going to perform. And that knowledge is what lets us engineer stronger, lighter, and more reliable steels for, well, everything from skyscrapers to spaceships.
This whole story is just a perfect example of science working exactly as it should. It's a fantastic reminder that progress isn't always about some giant, sudden breakthrough. Sometimes it's just about having the courage to take a second look at something we all think we already know. And it really leaves you wondering, doesn't it? What other scientific facts of today are just waiting for one curious detective to take a fresh look at the data?